See how we're doing on time. We got 21 minutes into the test. So hopefully I'm about half done. Looks like I am. I do have one to go back to. And you aren't having to talk through things, but I know it takes time to process some of this stuff as well. So this looks like it was a fairly long test. Dr. Bennett, our absent-minded professor, is riding his bicycle to class. On his first leg, he starts from rest, accelerates at a constant rate for 12 seconds. Afterwards, he gets tired, starts slowing down at a constant rate till he reaches class and comes to a stop. His second leg took him 50 seconds. How far did he ride? So we've worked problems like this. It's basically two constant acceleration problems in one dimension. So we'll work the two legs and calculate a distance for each and figure out how far he rode. So I'll label my first part right here. What do I know? Starts from rest. So V1 equals 0. Accelerates at a constant rate. So we're given 0.8 meters per second squared. We'll assume he starts at the origin, so our final S will be the distance he rode. So we're starting from the origin, and we know delta T right here. There was our A, here's our delta T, 12 seconds. Alright, so we are going to need to find both the velocity and the S2 here. Because we will need the final velocity of the first part to use as the initial velocity of the second part. But let's go ahead and find our S2 first. Again, we can look at our constant acceleration equations, and we just happen to have them on the test down here. You should have them on your equation sheet. But if I want to find S2, I don't know V2 yet, but I know all my other initial conditions. I'm going to use that equation right there. So it's going to be 0 plus 0 delta T plus 1/2 0.8 times 12 squared. That's pretty easy. Alright, so 0.5, whoops, get out of this thing. Okay, 0.5 times 0.8 times 12 squared. 57.6. So after 12 seconds, we've gone 57.6 meters. Let's see, the final velocity would be pretty easy. So V2 equals V1 plus AT. Again, that's rearranging the definition of A, delta V over T. So that's going to be equal to 0 plus 0.8 times 12. Oh, I think it's about 9.6. I'll double check myself on the calculator. 0.8 times 12. Hey, math in the head. Alright, so part 2. So we'll say V2 is equal to 9.6 meters per second. V3 we really don't care about, or actually we do care about. We know came to a stop. Okay, so V3 is 0. We knew he slowed down. We're told he slows down at a constant rate, but we don't know that, so the acceleration is unknown, and we know the delta T is 50 seconds. Alright, let's see. We know the initial S2 was 57.6, and we don't know S3. So again, we can solve this as long as we have a maximum of 2 unknowns. We really don't care about the acceleration, so let's look at an equation without acceleration in it. It's not that one, it's not that one, it's not that one. There we go. Alright, so we can find S3, I'll go ahead and write it down, S2 plus V2 plus V3 over 2 delta t. Okay, just switching my subscripts around to match my problem. So that's going to be equal to 57.6 plus, oops, that's right, 9.6 plus 0 over 2, and delta t was 50 seconds. Okay. Again, pull the calculator out. 57.6 plus 9.6 divided by 2 times 50. Be careful with your parentheses. In this case, I don't need them, but it doesn't hurt to put them in. 2, what was that answer? It went away. 297.6 or 298 if I go to 3 places there. And that's units of meters. Alright, so I'll write it up in the box here, 298 meters. A common mistake on this problem was to add this first part back into the 298. That's sort of double counting it because we've already included it right there. Alright, so we don't want to do that. The 298 is the total distance from the origin because we worked it in 2 parts, and our initial position of the second part was the 57.6.